Dear friends, this is Dr. Prasanna. This channel is open to cater the needs of aspirants of various competitive examinations, including entrance examinations of various states of India conducted for admissions to engineering, medical and science programs. JEE Mains, JEE Advanced, NEET, KCET of Karnataka are few examples of such examinations. This channel provides a series of lectures on topics of physics covering NCERT syllabus. I request you to subscribe this channel to make use of this social cause and to like this video if you feel it useful. Before taking up few examples of the questions or the problems being given in entrance examinations, let us understand few terminologies, starting with the definition of physics. The definition of physics gives you an idea that it is the study of nature and natural phenomena using the rules that are governing them. Physicists develop rules based on observations, experimentations and analysis. And while studying the course physics, we encounter with a number of quantities which are termed as physical quantities. And what is the meaning of a physical quantity? It means that it is a measurable property of a material or a system. We can find hundreds of examples around us for the physical quantity. Few are here. For example, length, mass, time, area, electric current, force, velocity, etc. Since this chapter is importantly on units and measurement, let me define the term unit. Measurement of a physical quantity requires comparison with a certain basic, arbitrarily chosen, internationally accepted reference that is called unit. In this lecture 1, let us look into a few systems of unit and also few examples of dimensional equations. In our daily experience, we can find that a bus is heavier than a bicycle. But exactly how many times? This can be answered only if a unit mass is chosen. Similarly, New Delhi is farther than Bangalore from Hassan, that's a small city in Karnataka. But by how many times? Idea of unit length helps estimating the distance of New Delhi from our native place or Bangalore from our native place. A physical quantity is expressed in two parts. First part gives how many times of the standard unit and second part gives name of that unit. Just take an example. In a statement, I take 2-hour duration of time to reach my college. This is the statement. In this statement, we are talking about the time taken in order to reach our college. That time is given to be 2 hours. Here, time is actually the physical quantity, whereas the numeric 2 is indicating that physical quantity is 2 times the unit of time. Here, hour represents the unit. Who decides this unit? Because we have to accept the system of unit or these units internationally, so that there is a body which is in short known as CGPM, which is also known as General Conference on Weight and Measures in English. Let us look into the classification of physical quantities. There are two types of quantities. One is known as fundamental, the other one is derived. Fundamental quantities, which are also known as base quantities, are independent of each other. The physical quantities which are independent of any other physical quantity is known as the base quantity or fundamental quantity, whereas the derived quantities are depending on the fundamental quantities. In 1971, CGPM decided 7 base units and 2 supplementary units as International System of Units, which is also known as SI units. It is a system of unit. Additionally, there are few other systems of unit which I take up in the next slide. The 7 fundamental physical quantities named by CGPM are listed here: length, mass, time, electric current, temperature, amount of substance, luminous intensity. The corresponding units are here. For length it is meter, for mass it is kilogram, second is for time, ampere for electric current, Kelvin for temperature, mole for amount of substance, and candela for luminous intensity. Their symbols are given here. L is the symbol, M is the symbol for the unit of length, small letter m, and kilogram, kg, is the symbol for kilogram per second, small letter s, and for ampere, capital letter A, Kelvin, capital K, for mole, mol, candela, cd. One has to remember an important point at this moment, that the symbol of unit must be expressed in the singular form. For example, in practice, some people say that if there is a quantity having 10 kilogram of mass, sometimes they express it as 10 kgs. This is completely wrong notion. Unit means it is 1. When it is unit, the symbol must also be expressed in singular form, or even while writing in a word, we have to express in singular form only. Meters, kilograms, seconds are the wrong methods, means wrong terms being used by many of us. While expressing the second also, some people write that it is SEC. That is completely wrong, because small letter s is the internationally accepted symbol. Similarly, while using the name of a scientist for the unit, in word, while writing that unit, one has to write every letter in lowercase only, whereas the symbolical representation is capital. For example, ampere is the name of a scientist, which is taken as the name of unit, wherein you have to express small letter a, start with small letter a, and symbol is capital A. Similarly, while expressing Kelvin, which is also the name of a scientist, you have to start with small letter k only. Of course, when we use this term, when we express Kelvin as the name of a person, we have to write with capital K, because it is the proper noun, Kelvin, this way. But for units, when we use the names of the scientists, first letter or all the letters must be in lowercase, small letters, and symbols must be exactly the ones which have been suggested by CGPM. We have to use them only compulsorily. And supplementary unit quantities are 2 in number, angle in a plane, solid angle. Radian is the unit of angle in a plane, and steradian for solid angle. So the symbols are given here: RAD for radian, SR for steradian. Now let us understand about the derived quantities. As I mentioned earlier, these quantities are the combinations of the fundamental quantities. That's why it is mentioned here that these derived quantities are expressed in terms of fundamental quantities. Their units which can be derived from the fundamental units are known as derived units. Just for the sake of examples, I have mentioned a few here. Area is a derived quantity because area is obtained by multiplying length and length of a square. For example, if you need area of a square, this is having length on one side, length on the other side. Also L value means all sides have equal lengths. Therefore, L into L gives L square. That is the area. That means meter is unit of length, and for another length meter, so meter multiplied with meter gives you meter square. So that this is the derived unit, and in symbolical form m square. And it must be small letter m. Capital M must not be used for the unit of length. Force, similarly, it is actually defined as mass multiplied by acceleration due to gravity. If you have studied mechanics, this may be understood. And the definition of mass and multiplication of mass and acceleration gives you the force. And acceleration is velocity by time. Velocity is distance by time. By substituting their corresponding units, one can obtain kilogram meter per second square in short form, kg meter per second square in symbolical form. This unit is also known as Newton. That's the name of the scientist. Hence, we are expressing the unit with all small letters, but symbol of Newton is capital N. Similarly, for linear momentum, kg meter per second, for pressure, kilogram per meter second square, which is also known as Pascal. So in this way, hundreds of physical quantities are there which have been derived by making use of the fundamental quantities, and these are the units which have been derived using the fundamental units. And few other systems of units which are in practice are CGS system, wherein centimeter, gram, second are used for the length, mass and time as units. Similarly, in FPS system, foot, pound and second are the units respectively for length, mass and time. Similar is the case for MKS system. Meter, kilogram, second are the units for length, mass and time. But presently accepted, internationally accepted system of unit is SI system. And while describing the unit of mass, SI unit of mass, I mentioned that kilogram is the unit, where kilo means it is a power of 10. We call this as the prefix. So for expressing the units, sometimes we use prefixes which are the powers of tens. For example, if you take resistance, if you go to the electricity chapter, we can find the concepts of resistance, which will be expressed sometimes in ohm, that is the unit of resistance. We will express it sometimes in kilo ohm, small letter k and ohm, and sometimes we represent capital M and ohm, which is known as mega ohm. So here this k and m are known as prefixes, which are actually powers of 10. That means kilo is 10 power plus 3. Similarly, mega is nothing but 10 power 6. In the same way, milli, if the power is negative, we have few other names of the prefixes. If 10 power minus 3 is there, we call it as milli, for which symbol is small m. So we have given a list here. For example, if the power of 10 is 18, it is named as exa, symbolically capital E. And for 15, it is peta, P is symbol. 10 power 12 is tera, 10 power 9 is giga, 10 power 6 is known as mega, 10 power 3 is kilo, symbol is small letter k, 10 power 2 is hecto, 10 power 1 is deca. Similar is the case for the negative powers. If the power of 10 is minus 1, then it is known as deci, symbolically small letter d. And if power is 10 power minus 2 is taken, its name is centi. 10 power minus 2 is centi. 10 power minus 3 is milli. Power minus 6 is micro. 10 power minus 9 is nano. So micro, mu is the symbol for micro, small letter m is the symbol for milli. Here one must not be confused. For example, when we express the thickness of some object as equal to 10 mm, one should not read it as meter. Here this is the prefix, which means it is 10 power minus 3. And the second m is actually the unit. That is 10 power minus 3 meter. That's the meaning. This is how one has to read mm. So it is millimeter. So small letter m represents milli as well as meter. We have to understand the context. Dimensions of physical quantities. This is the focal point of this particular lecture. So that let us understand what exactly the meaning of dimensions. A derived physical quantity is a product of different powers of the base quantities. That is another form of defining a derived physical quantity. So derived physical quantity is a product of different powers of basic quantities or fundamental quantities. I have taken one example here. In other words, the exponent of a base quantity that enters into an equation is called dimension. That is power of a physical quantity. In this case, I have taken the example of force, wherein mass multiplied by acceleration is the definition. And I was mentioning, as I was mentioning in the previous slide, the acceleration is defined in terms of velocity divided by time, and velocity is displacement by time, but displacement is measured in terms of length. Hence, I have put length by time in the place of velocity. So as a whole, if you see the definition of force, you are getting mass multiplied by length divided by time square. That is 10 power minus 2 if it is taken to numerator. So now mass power is 1, length power is 1, time power is minus 2. So dimensions of force are 1 in mass, 1 in length, and 2, that is minus 2 in time. And while expressing the dimensional equation, we need not bother about the magnitudes. We need not write magnitudes. For example, if force is 10 Newton, we need not express that 10, that numeric 10 in the new dimensional equation. And symbolical representation of a dimensional formula is in this form. Square brackets are used in order to represent the dimensions. And that is equal to capital M, capital L, capital T. These are the symbols of mass, length, and time. Other symbols are mentioned here. For length, it is capital L. For mass, capital M. So one should not have confusion with the symbol used here. Small m is the symbol for meter, but capital M, when it comes to the dimensional equation, capital M represents mass in the dimensional formula. And when it is a prefix, capital M represents mega. So one must understand these contrasts. Let us take a few examples of the questions being given in competitive examinations. I have taken 2 examples in this particular lecture, so which may cater the need of the aspirants who are taking such examinations. In this particular question, 2 lists have been given. Under the first column, in the first column, Planck's constant is mentioned as a first quantity, stopping potential, work function, and momentum. These are the 4 physical quantities. Here, one point that I have to recall is that we need a prerequisite for the one who is watching this video, that the knowledge of definitions of such physical quantities. Only if you have the idea of definitions of such physical quantities, then it is easier for obtaining either the derived units of those quantities or the dimensional equations. Right. So this is the particular question. Here we have to match the quantities given in the first list with the dimensional equations given in the second list. In fact, second one is the answer. If I simply say that the second one is answer, it may not be clear. Therefore, I give you the solution in the next slide. Here, we need dimensional equation for Planck's constant. Therefore, I take one simple example of Planck's constant being appeared in an equation. In fact, it appears in quantum mechanics while discussing about the Planck's law of blackbody radiation. We will encounter with this equation because Max Planck provided a relation to express the energy of a quantum of radiation or photon associated with the light, which is given by h nu, where nu is known as frequency, h is the Planck's constant. So the product of this constant and frequency is known as energy of a quantum or a photon. Anyway, so now using this equation, one can have an idea that ratio of energy to frequency is Planck's constant. Energy is kinetic energy, for example, expressed as half mv square, and reciprocal of period of oscillations is also defined as the frequency. Therefore, 1 by t is expressed here. Capital T is representing time period of an oscillation. Hence, now since we are not bothering about the magnitude, this 1 by 2 is not expressed in the next step. For mass, dimension symbol is capital M. It has power 1. Therefore, capital M power 1 is written. And velocity. Velocity is defined as distance divided by time. That is length by time for velocity. Therefore, velocity square takes L square by T square, or it is L power 2 T power minus 2. Hence, in this equation, you can see L power 2 T power minus 2. Similarly, 1 by T is nothing but T power minus 1. And if it is brought to the numerator, again, this becomes T power plus 1. So, T power plus 1, T power minus 2 gives you T power minus 1. Therefore, for Planck's constant, dimensional equation is M power 1, L power 2 and T power minus 1, this one. So that A is matching with the third one on right hand side. Similarly, let us take stopping potential. In photoelectric effect phenomenon, one will study about the stopping potential, wherein you can find one important equation that gives the kinetic energy of an electron as a product of charge of electron and stopping potential. So that stopping potential is energy divided by charge. Again, as I have taken in the previous case, half mv square is taken in the place of E, and charge is expressed in terms of electric current and time. The reason why I am doing all this is that we have to express the quantities in terms of fundamental quantities. Derived quantities must be expressed in terms of derived fundamental quantities. That's the reason why we are taking the definitions in terms of the fundamental quantities. So current is, electric current is basically defined as charge per unit time, charge by time. Therefore, charge, here in this case we are taking charge as small letter e, charge of electron. So E is therefore I into T, electric current into time. So for mass, power 1, L power 2 T power minus 2 for V velocity. For electric current, we use the symbol A, and for time, capital T having the power 1, therefore T power 1. On simplification, you will get this answer which is available here. So that stopping potential is mapped with fourth one. Similarly, This work function that also appears in the case of photoelectric effect, wherein product of h, that is Planck's constant, and frequency gives the work function. And this frequency is again reciprocal of time period, as I mentioned in the first case. So for h you already know the dimensional equation, and for t power 1 simplified format is of this form: capital M power 1, L power 2 and t power minus 2, so that the work function is mapping to the first one. Then momentum, which is the product of mass and velocity, so that mass power 1 velocity, as I indicated earlier, velocity is L by t, distance by time, so L power 1 t power minus 1. So this is available here. So it is mapping with 2, d is mapping with 2. So the answer is therefore second one. So although I explained a very physical quantity in detail individually, while solving such a problem in a competitive examination, you cannot work out every step, because you will find hardly 1 minute for finding the answer for such a question in the competitive examination. So that you must have the knowledge of all these equations, you must have these things in your mind itself, and you must be able to do some calculations in mind itself. If not, one has to write on paper and find the answer. Similarly, I have taken one more example wherein you can find physical quantities in one list, corresponding units in the other list, derived units. We have to match the corresponding units for the unit quantities of the first particular list. Of course, in this case also answer is in the second one. Let us verify it. In order to verify, I consider the definitions of the physical quantities. For surface tension in fluid dynamics, you can find a definition, that is force per unit length. Force is mass into acceleration. We have already discussed about obtaining the dimensional equation for force. Of course, in this case, there is no need to find the dimensional equation, because this problem is not demanding you to find out the dimensional equation, but I have worked it out just to make you understand how to obtain the dimensional equation even for surface tension. But as far as the examination is concerned, you have to recall the definition: force per length, and force must be taken in terms of the fundamental quantities, and corresponding units must be analyzed. Mass into displacement by time square is actually mass into acceleration. Therefore, mass is measured in kilogram, and displacement is measured in meter. Time is measured in second, so second square. Meter is the unit of length. Therefore, you can cancel the meter. Kg per second square will remain. Therefore, kg per second square is here. So surface tension maps with fourth one. Similarly, for pressure, in the next slide we can find it out. For pressure, definition is force per unit area. Again, force is appearing in the numerator, so I need not go deep into this part. And area is square of length. So unit of mass is kilogram, displacement meter, second square for time, and length is again meter square. So that this meter cancels 1 meter in the denominator. Kg per meter per second square. So this is therefore unit for pressure, and dimensional equation is given here. I am not explaining because I have already told you how to obtain the dimensional equation. So for pressure, derived unit is kg per meter per second square. It is here. Similarly, for viscosity, you can find the definition: force multiplied by time by area. The force dimensional equation is given here, and kg is the unit for mass, meter for displacement, second square, and again 1 second, and meter square here. On simplifying, you will get kg per meter per second. So kg per meter per second is here. Therefore, viscosity maps with this kg per meter per second, C with 1. Similarly, impulse, that is the product of force and time. So that mass multiplied by displacement by time square for force and multiplied by time. So unit is kg meter second square, in the denominator, second in the numerator. Therefore, this second of the numerator cancels 1 second in the denominator. So 1 second will remain in the denominator. Hence, t power minus 1 appears in the dimensional equation. Unit is therefore kg meter per second. So kg meter per second is here. So that impulse maps with second one. That is the reason why, since A is mapping with fourth one and pressure is mapping with the third one, answer is the second one. So one has to find the solution in this way in a faster pace. In the upcoming video, I will give you the details of errors in measurements, and I will take up a few examples of the competitive examinations, and we can discuss how to obtain the answer through solutions. Thank you all. I request you again to subscribe this channel and to like the video if you find it useful.